How's it going, Carter?
Good. How are you?
Not too bad. Hopefully we can get through some problems tonight and get y'all started on your homework stuff.
I'm excited that we have a little more time in this semester. I think the summer semester was a lot for a short amount of time.
Yeah. Summers are a nightmare. I had one teacher tell me they're all ingestion and no digestion.
I kind of feel that way.
Yep. Like I got it all in my mouth, but I don't know what to do with it now.
Yeah.
uh,
So is there only like eight people in this class? Is that how many there was on
yeah,
Tuesday?
it's only like eight. I think the number was 8 or 9.
Wow.
But yep, it's a very small number.
I guess like the fall is kind of like off to take physics too, right? Like most people take one in the fall and two in the spring.
Yeah, the enrollment's a little lower on the 240 or the 242 in general, just because it's so much harder, but it's still it's normally bigger than this, even for the spring semester. Oh, excuse me. Even for the fall semester. I said spring, but I meant fall.
Yeah.
Uh I'm going ahead and making chapter 17. I'm going to go ahead and make that due at least Wednesday for right now. Just because I've been having the problem of not being able to get there. Uh, get finished with chapter 17 in a timely fashion. So I feel bad and I want to make sure my students don't, get discouraged on their first homework assignment.
Yeah.
I have a quick question.
Yeah.
So I was trying to watch the lectures yesterday through Canvas, but the links for the YouTube site wasn't working.
Mhm.
Um, so I don't know.
Actually does work. There's a trick to it though. I thought I told that to you guys, but I might not have. When you click on the link, it opens up a new window in Canvas and it makes that sad face for a computer, like it can't link up. But up in the top of the window, or at least the top of the little window that normally would display the video, that's the name of the video. And then right next to it's this little box with an arrow. If you click on that little box, it'll do it. I'll show people in class today, but that's what you have to do. It acts like it's not going to do it, but it will do it. You just have to do that second button, which is, I don't know why it has it that way, but it's a pain in the butt.
Okay, thank you.
No problem. Sorry about that problem. I tried to mention it to everybody, but I'm pretty confident I didn't mention it to your class. But I did make a YouTube video on it, but I put it in here and you can't actually do anything about it because you have to know the trick to actually open the video. The things us nerdy people think is funny is kind of cute, I guess. We still got about 1 minute. It looks like 4 people, 3 people were in here other than me, so that's not very big. Feel free to ask me questions if you have them, though.
I have another question about the homework. Sorry.
Go for it.
So I took physics 1 at VPCC and I did it online the same way in Pearson. And I know that like after each question you get like 5 tries, and sometimes my professor would like make the percentage go down, like the credit for the question go down every time you answered it wrong. Are you
Right.
gonna do the same thing, or just like if you get it right, you get it right?
Let me double check how I do grade these. Let me I think what I have is you might actually lose points after multiple trials, but I can't remember if I changed it that way. Let's see. I'm gonna find out in a second. Grading presentation settings. There it is. It says allow students to take assignment up to 3 times and keep the best score. Show assignment score to subject to student. It does have that. Late answer submissions, that's to reduce the credit by 4% over each day with a maximum of 20%. Question attempts. Show students whether an answer is correct or incorrect after each answer attempt. If students exhaust all attempts or give up, show the correct answer immediately. Limit the number of attempts per question to 6. Of course, that doesn't include multiple choice. Oh, no, I did deductions for incorrect multiple choice. Deduct credit for each incorrect answer before the last attempt deduction. So that's what I do on the multiple choice. Deductions for any other incorrect questions, I take off 2% each time you get it wrong.
Okay, thank you.
No problem. So at least we have that on the video now. So that's something that they'll have access, the other students will have access to. I do allow you to print it. I allow to rework for practice. And that's basically it. Okay. So it still looks like we're way up to 5 people now. I really should look and see how many people we have in the actual class. I thought last time I looked it was 9. But I'm not sure. I still got it's actually past time to start, but I wanted to see if more people will come before we get started. So let me check the roster real quick. Yep, it has 9 enrolled. That's cool. All right. So does anybody have any other questions? All right. So I've already had one question, which is a very good question, and it's exactly the kind of questions I want from my awesome students. The problem is it's because I did not actually tell y'all something I was supposed to tell you. So I'm going to go ahead and show that to you now, just as soon as I figure out how to share this particular screen with everyone and make sure I don't have all these other ones there. Okay, so that looks good. Here we go. Let's see if I got it under helpful links. Not there, not there, not there. Here either. So it's not on that one. See if it's here. No, 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 no. Nope, not there either. All right, I guess I'll just do it with this. Okay, so what I'm going to do, everybody, is I'm going to share the screen from my Canvas page right now with you guys. One student has mentioned they had some difficulty loading up the video, and that's very much expected from me. I try to make sure I tell everyone. I evidently forgot to tell you guys that on this one, but right now you're looking at week 1. There you go, you, my yawn. You're looking at week 1, which has the wrong date on it. I didn't change that yet. But in it has all these little chain links are actual links to my videos on my YouTube channel. Let me just click on one to show you. So when you click on it, this is what happens. See the little sad face and YouTube refused to connect right there? Well, it does work, but it looks like it's not working. And I'm not sure why it does this, but it always has. So I'll just tell you, when you click on that and you get this, what you want to do is go up here and click on that little box. Yeah, it might actually work when you click on the title too. I'm not sure. I just know I clicked on that box one time. So let's try clicking on the title and seeing what happens. Yep, it looks like it works for the title as well. So you can see there, and I'm sorry that stunning man there. But anyways, so yeah, that actually does get it for you. So that's what you do with these videos when you're trying to get one and it comes up this face. I've always been clicking on that little thing, but come to find out it works fine to click on the title as well. But when it does it, it does open up an entirely new tab. And I suspect you're going directly to YouTube, not staying in Canvas. Ugh. So whatever it causes that, that's the result of it. Everybody get that? Did I miss anyone? Anybody not catch what I was saying about it? Okay, I'm going back to the modules now, and this is your invitation for the Zoom meeting, of course. This is that generic stuff. These right here, the interesting science-related links and documents and helpful links and documents are good stuff. I'll be updating that since tomorrow is the first day I have that I don't teach yet. That'll allow me to finally catch up with the syllabus and all that good stuff. So I'll have all that for everybody. I'll also have this helpful links and documents filled with the equation sheets, which I already have some of them, like 17 to 31 and 1 through 14, or 1 through 11, 14, 15, 36. That's the allowed equation sheet. There was an error on it. I got to make sure that's the right version because I found an error on it. And actually, I can probably look right now. Let's see what it looks like. So this is the equation sheet you'll have access to when you're taking your tests, whether it be online or face-to-face or whatever. You're actually, of course, obviously you're allowed to have anything out when you're taking the online test, but in the face-to-face in the face-to-face test, you could have this as a printout and it would save you a lot of time. Uh, you're just not allowed to write extra stuff on it. Okay, so don't do that, or I'll have to go through one by one and check all the extra stuff and see if that's acceptable, because it might be something minor. But generally speaking, don't write on it or anything, because those are exactly what I'm allowing you to have. The only thing that I left out is I told the students at one time that they could actually write down what each variable is, like V is for velocity or omega is for angular velocity. That's the only thing I told them that you can write. Oh, excuse me, that you can write. No, this is the fixed version because it was that 3 right there that was missing. So this is the fixed version. And of course, it covers the entire semester. So it's got a lot of stuff in there that you don't recognize, when in fact, the first chapter is going to deal with just pretty much this stuff. Well, actually, the second chapter. So anyways, that's there. So all of this stuff will be updated and that sort of thing by Monday, but I'll be doing it on Friday, Friday, Saturday, and Sunday. So anybody have any other questions before we get started? All right, well, I'm going to go ahead and stop sharing. All right, we got another student coming in. We're already up to 7 students. Woo-hoo. So I'm going to open up my iPad. I'm going to open up my GoodNotes. And I'm going to get to the appropriate page so I can use my GoodNotes, and then I'll share with you guys. And of course, I'm obviously yawning again for some reason. And today is the 29th. So I'll make sure my date's corrected on here. That's the 29th. And now I got to make a copy of that, or else I'll have to make a whole new one next time. Duplicate. Boom. All right, so I'm going to go ahead and share my screen with you guys, and I'm using my iPad screen. So it's not this page. There it is. Okay, so this screen should come up. There it is. Everybody sees that now. So that's the screen where I'll be taking my notes and all that good stuff. And to date, we haven't really covered anything. So what I want you to know is we're going over. Remember how I told you I will tell you what chapter we're doing each time we do it. We're covering chapter 17 now, and that's the only chapter we've covered. So any homework assignments, any homework assignments for any chapters other than 17 that all of a sudden pop up and say they're due, you can ignore it, even though Pearson suggests it is. Okay, so just it's only the chapters we covered that will ever be coming due. And even then, I usually require that I finish it in some sense before it's actually due. So just remember that, because in the semester it's going to go quite differently. But what I want to start off with is talking to you about matter and how matter is made. You've probably all had earth science or any kind of physical science in high school or grade school. You've probably had a biology course in high school or grade school, and you might have even had a chemistry or physics course. But the main thing is, in all of those, you probably should have learned at one time that atoms look a little bit like a solar system. So there's this, what we call the Bohr, B-O-H-R model of the atom. And with the Bohr model of the atom, you have a little highly dense nucleus. And that nucleus is like 99.99% or more of the entire mass of the atom. And that's not unlike our solar system. Our solar system has the sun being about 99.99% of the entire mass of the solar system. And then you have in our solar system all the planets orbiting essentially in the same direction and almost in the same plane. We're going to have all these electrons orbiting around the nucleus. And of course, the nucleus is made up of protons and neutrons and stuff like that. But we're going to have electrons orbiting it. And this is really, really, really not to scale. Okay, it's not to scale in the sense that if you were to blow up a nucleus, in other words, zoom in on it in a camera photo until the nucleus became the size of a grape seed, and hopefully y'all know how small grape seeds are. They can fit between your teeth. They're so small they can fit between your teeth. Now, if you take that grape seed and you put it at the 50-yard line of the Washington Commanders football field, then the first orbit for the electrons will be way past the parking lot. So it's like a factor of 10,000 bigger. The orbit of the electrons is about a factor of 10,000 larger than the nucleus. So that's a really big difference. So when you talk about matter, like they did in the very old movie Honey, I Shrunk the Kids, they said matter is mostly empty space. They're exactly right. The reason why I need to tell you about this for this particular instance is I want you to understand that these atoms don't necessarily stay in the same plane. So, or these electron orbits don't stay in the same plane. So some of them could look like this, and some of them could look like that. But the main thing is they have the first one quite a big distance away from the nucleus, and then the next one's quite a whole lot closer to that orbital than the previous one was to the nucleus. And then the next one will be a little bit closer to the previous orbit than the other one was, and so on and so forth. But the outermost electrons are called the valence electrons. And because they're so far out, they're generally not held quite as tightly as the inner nuclei, as the inner electrons are. So that's sort of the picture I want you to have for the atoms in matter. Now, if you have a substance made of something other than a pure element, then it has, it could be a mixture, which we don't really study that much, but like you can think of a salad, for instance, as a mixture. And if you think about that, a salad has a lot of parts. It has like cucumbers and onions and radishes and lettuce and tomatoes and bacon bits, at least mine does, and cheese and stuff like that. So you might think, well, what's the smallest part of a bowl of salad that you can get and still call it a salad? Well, that's not a really well-defined characteristic. So that's sort of the nature of a mixture. Elements, on the other hand, you can keep taking a chunk of an element. So, for instance, if you had a big pure copper rod and you could cut it in half, and this is actually the thought experiment that Democritus did. And he imagined that you could cut it in half and then take one of those halves and cut that in half, and then take one of those halves and cut that in half. And he imagined two scenarios. One scenario was that you could do that forever. And the other scenario was you couldn't do that forever. And in fact, you eventually run into a smallest part that you can no longer split. And in fact, Democritus from ancient Greek uh, named that an atom. And as best I can tell, the little bit I've studied with ancient Greek, a as a prefix means not or non, something like that. And tom means divisible or able to be cut. So when you come up with the word atom, or atom, that's supposed to be an indivisible part. So that's what the smallest part of an element is the atom. If you were to take a compound like water, for instance, let's imagine keeping it really, really cold and freezing water, and then you have a big solid chunk of pure water. You cut that chunk in half, then you take one of the halves, you cut that chunk in half. You take one of the halves, you cut that chunk in half. And you keep doing that over and over and over again. And Democritus's idea stands again, only this time you get to a smallest part that still behaves like ice, and that smallest part is a molecule. The other one was actually an atom. Of course, Democritus would have considered it to some extent an atom as well, because they didn't know necessarily about exactly what atoms were. But in both cases, we know it's technically wrong because we can clearly break up H2O into two H's and an O. And you probably know that we have particle accelerators and stuff like that that can break up parts of an atom. Or you know that you can even, drag your feet across the carpet and strip electrons off of the atoms. So you can definitely take apart atoms, but we've changed it, like I said, to say that at that smallest part, it still behaves like the material it was. So in the case of a compound, the smallest part that retains its identity as that compound is a molecule, which is made up of two or more atoms. And it could be two or more atoms of different types, or for instance, there's something called molecular hydrogen, molecular oxygen, molecular nitrogen, that naturally just occur in groups of two because they're just not satisfied with their electron configuration. Hydrogen's one short of being full, having its outer level full. So hydrogen naturally bonds with hydrogen to make H2, and that's the regular way we run into hydrogen in our atmosphere. Oxygen does the same thing, and nitrogen does the same thing as well. So when you're actually doing stuff and you got to calculate, for instance, the molecular formula of hydrogen or oxygen or nitrogen, at least in our atmosphere, you have to assume that's H2, N2, and O2. Okay. So that's basically one of the ideas. Now, the other big thing is, yes, you can break it apart, but Democritus suggested this was the case, and it was just basically based on the idea that he thought it was crazy to think you could cut that over and over and over again forever. And even that is technically correct because we do know that you can break open an atom, but then you break open the atom. What did you do? Did you just knock the electrons off and leave the nucleus? That could be a case. That's not very big deal. But then can you break open the nucleus? Well, we discovered, around the shortly after the discovery of quantum mechanics, we started probing the nucleus as well, and we were able to break that apart. And that turns out to be made of protons and neutrons. And then you say, well, can you break apart the electron or the proton or the neutron? Well, the electron turns out to be an elementary particle, And in fact, we don't think it has any physical size. It's a point particle. Like every time we try to measure how big it could be, it's always smaller than our finest measurement. So to date, we're treating it as if it's a point particle. And that's what string theory and that sort of stuff's about. The proton and neutron, however, are actually made up of quarks, so they can be broken down into smaller particles. And then the quarks turn out that they can't be broken down into further particles as far as we know. Okay. So that's a picture of matter. And when Democritus did this, he looked for evidence to support or reject his claim. And the evidence, some of the evidence he offered was, for instance, if you're walking in Athens, say, and you go by a bakery, there's a good chance you're going to smell that wonderful, delicious smell of bread. And what he pictured that was, or what that picture was pictured as being, was the literal atoms that make up the bread had broken off and wafted through the air and ended up going in your nostrils. That turns out to be right. So I'll leave it to you guys. You know, I'll leave my seventh grade mentality out of it and choose not to give you a full description. But you can imagine anytime you smell something, what's literally happening is a molecule of that thing you're smelling has entered your nostril. So yay! But anyways, so he was right on the money. It turns out that is exactly how smells work and how we experience them and that sort of thing. The other thing about the atoms and molecules is that when Richard Feynman, a Nobel laureate, a Nobel Prize winning physicist that retired ultimately from Caltech, he had won a Nobel Prize. And of course, like all Nobel Prize winners, they're asked a lot of questions about things that don't matter. And sometimes they're just asked about questions about their field, which is a good thing. I mean, that's where they really are experts, is in their field. And he was asked, what would you leave if there was a time where this was like a post-apocalyptic world? We had like World War III, all of technology and the brain power that we had on planet Earth has been destroyed, and you could leave one sentence for future generations. What sentence would you choose to leave so that humanity could get very close to what we are technologically right now, so that they could come up with the beautiful things we've come up with for, treating cancers and stuff of that sort? And he said, I would let them know that there are small particles, atoms, that make up everything. And sometimes those atoms come together and make up molecules, and they jiggle around in space at this very, very small scale. And the higher the temperature they have, the more rapidly they jiggle. And in that sentence, he says it was the most amount of knowledge you could possibly get in a single sentence. In fact, that Feynman quote happens to be in some of our helpful documents or interesting stuff. One of those two links, you'll find it in there. So I sort of tried to paraphrase it, did not do a very good job. But the point I'm making here is we're opening in chapter 17 by using the premise that atoms exist, and what can we discover based on that. So now that you have that as a little bit of feeder, I want you to think of atoms and molecules as if they're the smallest part of a particular substance, like I just explained to you. And it looks like y'all have go ahead and typed your, no problem, Hannah. Looks like y'all have typed your first and last name. Thank you for doing that. Everybody, please do that if you haven't already. That way I'll have you for roll. But yeah, we're picturing atoms and molecules as they're really, really small. You could even picture them as being infinitely small point particles, or very close to infinitely small compared to everyday life. In fact, they turn out to be around 10 to the negative 10th meters in size. And the nucleus, for instance, tends to turn out to be around 10 to the negative 14th meters in size. So they are very, very small. And you can sort of picture them as you just can't break them apart, and they do jiggle. And if you're talking about the solid state, it turns out that they arrange themselves in a lattice. So if you want to think about a lattice, try to imagine a chain link fence. You know how it has a aluminum, it goes down like this, and then it loops this way and goes down diagonally the other way, and then the other way and the other way. And then another piece comes in and loops right in there. So it makes these little diamond patterns. Well, everywhere you've got an X where one wire comes this way and another wire comes this way, that little X spot would be a place for an atom, for instance. And then if you imagine that those little wires that run from that crossover spot to another crossover spot are actually the bonds holding the adjacent atoms or molecules together, then you've got at least a two-dimensional picture of a lattice. Now, if you imagine that there's not just one of those little fences, there's another one right behind it, and connecting each of those atoms in the front fence is another piece of wire, if you will, that's connecting to the atoms behind. That again is the bond of the atoms on that first layer to the atoms on the second layer. So now you've got a three-dimensional structure. And since they jiggle and since they speed up jiggling when the temperature gets higher, you can imagine if you're starting with a solid, you have the molecules like this. They're just doing this sort of thing. Well, they're doing that because they have some kind of force of attraction between them that's holding them together. Now, if you add to that so much energy that they start jiggling more frantically, you'd probably reach the conclusion that the distance between them is going to be a little larger in that case because they're moving so rapidly that the force is a little bit overwhelmed and has to renegotiate exactly where it's at equilibrium. So it'll have an equilibrium position instead of here at the lower temperature. Now it might be here at the higher temperature. And if we go to a higher temperature still, it might be here. So from that idea alone, we've already reached the conclusion that things expand upon heating. And I'm going to give you an equation for that linear or thermal expansion. So that's one of the conclusions you can make. Another conclusion you can make is if you keep going up and up and up, eventually that force of attraction between adjacent atoms or molecules is going to be so overwhelmed that it can no longer hold the atoms or molecules together. So they're going to jiggle so much that they start breaking off. And that is, in fact, what happens when we transition from a solid to a liquid. At the liquid point, they've gotten so far apart that the molecular forces or atomic forces that were holding the two molecules or the two atoms together is too small to hold them together anymore. But there's still some affinity. So it's highly likely that this atom and this atom, which might have been used to be next to each other, when they first break apart, they might actually stay around each other quite a bit for a little while. But it's just a toss-up as to when it's going to come so close to another atom or molecule that this guy leaves and starts hanging around that atom or molecule, and then that guy leaves and starts hanging around another atom or molecule. So it's almost like you could think of it like the distance between them is even bigger than it was when they were a solid, and that now, instead of them being individually bonded, you could almost picture like the atom got bigger and now the atoms are rolling against each other like bowling balls in a ginormous bucket. Okay. So if you can imagine that, that's actually the liquid state. So there's still a little bit of attraction between the adjacent molecules or atoms with molecules and that sort of thing. And that is what the liquid state is. If you continue, though, of course, it's going to become more and more rapid motion with higher and higher temperatures. So the higher the temperature gets, eventually even that is going to stop. So you won't even have this molecule and this molecule or this atom and this atom. You won't even having them spend a microsecond together because they're going to be so rapidly moving that they're rapidly running away from each other and way farther apart than they were in the gaseous state. And in fact, there's almost like no upper limit about how far apart they can be. So in that sense, it's almost like you could take, let's say a 1 millimeter by 1 millimeter by 1 millimeter cube of atoms of gas, and you could put that in a sealed room that's 30 feet by 30 feet by 12 feet, and that gas would still in some way fill the whole space. That's what I mean by this, like almost no limit. We know that you can't technically really do that. It's not going to be smooth throughout the whole thing, but you'd be surprised how much space or how much volume a small amount of gas can cover. It's so prevalent that we can more or less pretend that that is exactly the case, even though it's not. Okay. at least for a lot of problems. So that's some information we got from just thinking about the atomic theory of matter. And the atomic theory of matter, though, Democritus suggested it. There may have been other people in other cultures beforehand, but that's one we know of. And if I remember correctly, that might have been 300 or 400 BC, what we now call the BCE, before the Common era. So that's roughly when the idea of the atom came up. But lo and behold, you probably don't know this, the actual conclusive evidence that atoms existed did not come until 1905, when a fairly obscurely known scientist by the name of Albert Einstein wrote a paper on Brownian motion. And that Brownian motion paper was Einstein applying what we call statistical mechanics, which is probably the single most powerful tool we have in physics. But he applied that, taking into account what we know about molecules and atoms, or what we believed about molecules and atoms at the time. And using that statistical mechanics, he was able to predict some stuff about what we knew as Brownian motion. Scientists by the name of Brown had discovered that when you had little individual grains of pollen sitting on top of a sample of water, the little individual grains would they would sort of dart off in really weird staggered patterns. So they'd go, kind of rapidly in a straight line, a very short straight line, and then rapidly in an entirely different direction in a straight line, and sort of do that over time. That was called Brownian motion. And at the time, some people thought that might be a matter of life. In other words, because the pollen grains came from plants, which were living, they thought that might be sort of like related to the fact that it was a living creature. Even so much as maybe it had something to do with the soul or something like that. Not quite as bad as the frogs that came up later when we learned about the galvanic process, where you could actually just take two dissimilar metals and stab them in the thigh of a frog leg, even when the frog's not attached, and the frog leg would kick. Okay, so that was another time where we thought it might be our evidence, for instance, of like a soul or something. But anyways, neither of those turned out. We haven't had to make that hypothesis yet, but some of us still go along with believing it. So in this process with the Brownian motion, how did they put the life question to rest? Well, they did it with dust particles, and they found out the same thing happened with dust particles. And no one believes for 1 second that dust particles are made of life. So that settled it. It was Brownian motion, and it is not related to life. And then Einstein basically wrote a paper sort of like saying, hey, if you observe this Brownian motion, it should behave this way. And then all it took was someone to do the experiment that he suggested. And if his experiment matched Einstein's theory, the way it was done with statistics would suggest that either Einstein got so lucky that he sort of like won all the lotteries in all the countries for like a million years straight. So that's the odds of him winning all those lotteries in all those countries for a million years straight is about what the odds would have to be if he had happened upon the right answer with using the wrong technique. In other words, not knowing that, not showing that atoms exist. So that was a really big nail in the coffin for the atomic theory of matter. And he could have, of course, won the Nobel Prize for that in 1905. But it turns out that same time, he also had a paper in 1905 for the photoelectric effect, which is basically when you shine light on a metal, a pure metal, it actually could generate electrons moving through it and create some kind of current. And he used Planck's hypothesis for that and was able to basically explain that phenomenon. And because of that, he did end up winning the Nobel Prize. And because of that, that was also the second paper that created quantum mechanics. So Planck did the first one and Einstein did the second one, even though Einstein really never accepted quantum mechanics till the day he died. In fact, they found in his notebook on his deathbed, he was still trying to come up with field equations to get rid of quantum mechanics literally the day he died. Okay. In that same year, by the way, he wrote another paper on something called the electrodynamics of moving bodies, which was his special relativity paper. And not only that, that obviously could have won him the Nobel Prize if people believed him right off the bat. But the next day he discovered yet another thing and sent it as an addendum. And that thing was E equals MC squared, which explained to us how atoms, or excuse me, how the sun worked. And it was related to, of course, atoms. Uh, Before that, we really had no definitive understanding of exactly how the sun worked. What we had was a historical book that was really uh, well respected and understood. And that book suggested the universe might be a few thousand years old. If you go through the book of Genesis and you look at those begats, where Adam begat such and such at such and such an age, and then Adam's son begat such and such at such and such an age. If you add up those ages and keep moving forward, counting those years up until you get a historical figure that you're familiar with, that we know actually existed in history, and we know their date, then you can predict when the universe was created. And that's what many people had done with the Bible. And it seemed, because once you get up to Nebuchadnezzar, we know exactly when Nebuchadnezzar was born, when he died, and that sort of thing. So once you get there, you can just dial the thing back, and that's the beginning of time. And they even suggested it was a Tuesday or a Saturday or something like that. In so doing, they basically said, well, the universe is probably less than 10,000 years old. Well, Lord Kelvin had done a calculation assuming that sun, which looks like a big ball of fire, a very smooth fire, of course, but if you look closer, you'll see something that more looks like flames a little bit, if you have the right type of telescope and stuff. So Lord Kelvin had said, let's imagine that since we know the weight of the sun, let's imagine it's a chunk of coal, because coal is what we use for our power. And he had done a calculation and discovered that that should probably last on the order of 50,000 years. I think it was 50,000, might have been 50,000 to 100,000 or something like that. But either way, since our historical record was the Earth was about less than 10,000 years old, 50,000 years is great. The negative side was we were just starting to get into areas of science in geology, in biology, of things that were pointing to the Earth possibly being hundreds of thousands of years old, if not millions of years old. If that was the case, then we got a lot of explaining to do. But luckily, that 1905 is the time that Einstein comes along and writes E equals MC squared. And we automatically can assess that the sun is going to live for about 10 billion. That's B as in billion, as in Billy. Okay. So it's going to live for 10 billion years roughly. So that's sort of a little bit of history of the atomic theory and how it was proven, and what Einstein's role in that was, and all of that we need for the underpinnings of this chapter 17. So I would like to ask you guys a question before we get started on the next part, or as part of the next part. Can anybody tell me what you think the units are on the periodic table? For instance, when you look on the periodic table, you'll see hydrogen has a mass of 1.007 something, something, something. Does anybody have any recollection of what the unit that mass would be in?
Isn't it grams per mole?
Yeah, thank you. That's exactly the way I put it. It's weird because I keep getting all these students that are giving me the other answer. I think they're actually reading the book ahead of time, but yeah, that's the way I grew up with it. It might be because the first robust science I got where I had to do any calculations was high school chemistry, and that's what we learned. It was a gram per mole. So if you took the number of grams of hydrogen and divided it by the grams per mole of hydrogen, that would tell you how many moles of hydrogen you had. Or if you had water, which is two hydrogens and an oxygen, that would be 2 grams per mole for the H2, and then 16 grams per mole for the oxygen. So that would mean 18 grams per mole for a mole of water. So if you took the number of grams of water you had and divided it by 18, that would be the number of moles of water you'd have. And remember, moles is the number 6.022 times 10 to the 23rd. That's basically what a mole is. It's that many atoms, or that many molecules, or that many frogs. If you had a mole of frogs, for instance, or a mole of moles, if you had a bunch of moles, it would have to be 6.022 times 10 to the 23rd. So that's obviously what you know of as Avogadro's number. So here's the neat thing. It turns out that yes, grams per mole is a perfect measure for that mass. but there's actually another as well, and I can make some sense of it in a second. And you're going to kind of be bothered because here's another number you got to know. The other unit it could be is something called the atomic mass unit, or the universal atomic mass unit is another way, but they just say a lowercase u. And therefore, when you look at carbon, it says 12.011. That could be read as 12.0011 grams per mole, or it could be read as 12.011 unified atomic mass units. And that specifically talks about the mass of a single atom of carbon. Now, let's back up a little bit and let you know that the individual masses that are printed on a periodic table aren't really the mass of any particular isotope of hydrogen or oxygen or anything like that. It's actually a weighted average. So when you look at the atomic mass of carbon being 12.011, what that really is you imagine all the isotopes of carbon that exist in nature in our atmosphere. And that would include, of course, carbon 12, carbon 13, carbon 14, maybe even carbon 15, carbon 16. I don't know. I do know carbon 12, 13, 14 at least. And then you say, okay, well, how prevalent is carbon 12? How prevalent is carbon 13? How prevalent is carbon 14, and so on and so forth? And what we find out is probably the vast majority of atoms of carbon that you run into on a daily basis within our atmosphere is carbon 12. So maybe that's 98%. And then carbon 13 might be 1%. And then carbon 14 might be 0.5%, and carbon 15 might be 0.25%, and carbon 16 might be 0.25%. So that they all add up to be 90%, I mean 100%. So now if you take the mass of carbon 12 and multiply it by 98%, 0.98, and then you take the mass of carbon 13 and multiply it by 1%, 0.01, and keep doing that with each of the isotopes, and then divide that whole sum by the 100%, then that's the 12.011 you'll get. So if you didn't know that, that's something you should know, just being someone who's interested in science. That's a fact you should know. So if you actually wanted to find out what the mass of a particular isotope is, what you'd look is look at a chart of nuclides, which is the chart that nuclear physicists, and more specifically physicists in general, use. In some sense, maybe more so than we use the periodic table. And that's sort of a bragging point for us physicists when we go to pick on other scientists like chemists. One of the things we might say is, we know the periodic table has about 100 elements, whereas the chart of nuclides has about 1,200. So we're 12 times smarter than chemists. Obviously, we don't necessarily, well, some of us believe that, but we don't generally believe that. We just like to say things like that. We have a lot of neat little things where we pick with other scientists. I'll tell you some stories about that later too. So that's the big picture of how the periodic table works. And now I'm going to tell you why that makes sense, that the mass of 12.011 grams per mole, which we're just going to call 12, and we're going to pretend like it's carbon 12 that we're talking about, because when they decided to make up this unified atomic mass unit and stuff, what they chose to do is they decided to call carbon 12 a atom that had a atomic mass unit mass of exactly 12.000 for an infinite number of decimal places. So whatever happens in the future, no matter how many more decimal places we get regarding the mass of carbon, we're always going to set carbon 12 to be 12.0000 as long as we can, because that was the original standard that we set for the atomic mass unit. So carbon 12 is supposed to be a flat carbon or a flat 12.000 atomic mass units. Now, if you think about that, you know that a Avogadro's number of carbon 12 atoms would have a mass of 12.000 infinite number of decimal places grams per mole. So a mole of them, Avogadro's number, would have a mass of 12.00000 grams. Now, if you wanted to know the mass per atom, then you just take that 12.0000 grams and divide it by Avogadro's number, and that would give you exactly the mass in grams of the carbon 12 atom. As you might suspect, because what I just finished telling you, that number becomes 1 divided by Avogadro's number. So if you take 1 and divide it by 6.022 times 10 to the negative 23rd, or excuse me, times 10 to the 23rd, you will get 1.6605 times 10 to the negative 24th, which is the unit conversion between the atomic mass unit, at least in grams, to 2 grams. If you wanted the kilogram one, which is what your book is giving you, you just divide that by 1,000, you get 10 to the negative 27. So that's the big picture. Now that I have that, I'm going to go ahead and share my screen again with you so that we can make use of that. So what we just discovered is that carbon 12, which implies 6 protons, 6 neutrons, and if it's neutral, implies 6 electrons. Okay. So the 12 actually means the total number of protons and neutrons. And if you look at the periodic table, hopefully you've all figured this out or had a chemistry course where they taught it to you. But hydrogen has the atomic number 1 because it has 1 proton. And it turns out, from what we learned from quantum mechanics as well as what we thought before that, it turns out that really the number of protons is pretty much all that matters in deciding how a particular element's going to behave when you try to combine it with other elements, as we do in chemistry. So hydrogen has 1 proton, and one isotope of hydrogen would be H1, and that's just called hydrogen. And that's basically a single proton with a single electron orbiting around it. And if you happen to strip that electron from that orbital, it's still hydrogen. It just happens to be hydrogen with a positive 1 charge. In other words, it still behaves like hydrogen. You can still take 2 of those and bond them with oxygen, and so on and so forth. Of course, you'd need the electron, extra electrons to fill the octuple or octupole orbital of oxygen. But other than that, you're good to go. Okay. And then the second element, of course, is atomic number 2, and that would be helium. And the third would be lithium, and the fourth would be beryllium, lithium, beryllium, yes. And the fifth would be boron. The sixth would be carbon, because carbon has 6 protons. Okay. Now, other isotopes, for instance, of hydrogen, one of them would be deuterium. And deuterium, notice that sounds like the old Navy SEALs movie, Part Deux or whatever. Actually, I think that was a ripoff of the old Navy SEALs movie. But anyways, the deux sounds like 2, and that's because it's actually called hydrogen 2, because it has 1 proton and 2 neutrons, or excuse me, 1 proton and 1 neutron, which means it has 2 nucleons. That's why it's called hydrogen 2. And then there's tritium, and tritium has 2 neutrons and a proton in the nucleus. And you can see why that's called tritium, because again, tri, like a tricycle, has 3. So those things behave just like hydrogen. So like you've seen, for instance, H2O, well, you can also use H2O made out of deuterium. And that's one version of heavy water. You could also use H2O made out of tritium, and that's an even heavier version of heavy water. And that's true for all of the isotopes of the elements, and that's what they're called. The different versions of the elements with different numbers of neutrons are actually called isotopes, isotopes. Okay, so carbon 12 has a mass. The mass of the carbon atom is equal to, of the carbon 12 atom, is equal to 12.0 with a line over it, U. Okay, and U is defined to be basically 1 over Avogadro's number, which equals 1.6605 0.0605 times 10 to the negative. In this case, it's going to be, I think, 24. Yes. Grams. But you could also say it's 1.6605 times 10 to the negative 27th kilograms. So you don't have to memorize a new conversion factor. You can just use your Avogadro's number that you already had, and that gives you an idea. So now that we have that epiphany about how the atomic mass in the periodic table gives us the mass of the atom or the mass of a mole, we can actually do something kind of neat with that. So for instance, it turns out copper atoms have a mass of 63 U, and copper has a density. Whoop, I had an extra hump in my word. Has a, whoa, did it? Has a density of 8.9 times 10 to the third kilograms per cubic meter. Use this information to find how far apart atoms of copper are in solid copper. Now, technically, that 8.9, that 8.9, I don't know why I put an E on there. That 8.9 kilograms per cubic meter is the density of copper at 20 degrees Celsius. If you go up to like 25, it's moderately different. Should be a little bit less, but the main thing is we have it for a particular temperature. Okay. So how are we going to do this? What we really want to know, is the number of meters divided by the number of atoms. So that's really what we're looking for, because if we had that, then we basically have the distance between adjacent atoms, or that's at least one way of thinking about it. I'm not sure that's the way you want to think about it, but it's a way you can think about it. So what I'm going to do to solve this is I'm going to imagine a cubic chunk of copper like this in that sort of lattice that I was telling you about earlier. And these lattices are things that we do actually work with in science. In fact, if you took a solid state physics course, a good fraction of the beginning of that course is really about you figuring all the different types of lattices that can occur and working out the geometry of them. So what we're going to imagine is that I've got little carbon atoms lined up along that side. And this might be a number of carbon atoms in one. And then you got a bunch of carbon atoms lined up this way. This one might be in two. And then you got a bunch of carbon atoms lined up this way, and this would be in three. And in fact, what I'm saying there is, there's a whole line of carbons right here, and then there's a whole line of carbons right here. So there's another carbon, there's another carbon, there's another carbon. And the reason why I point that out is so that you could say this is number of atoms equals N, which is going to equal N1 times N2 times N3. Okay, so that's why I pointed out that me listing the atoms lining up like that is equivalent to, if you wanted to count the ones on the front face, you'd multiply N1 times N2. And then you'd say, okay, well, how many planes like the front face are there in going from the front face to the back face? Well, there'd be n3 planes there. Now, we could imagine a scenario where it would be n times n times n, lowercase n's, and each one are the same. And that might actually be what it is for copper. But the main thing is it doesn't matter too terribly much. We're going to work it out anyways. The other thing I know, of course, about this is the density of copper is 8.9 times 10 to the third kilograms per cubic meter. And we know that the individual atom of carbon 12 has a mass of, why I say carbon 12, stupid head. The individual mass of copper is equal to 63 U. Okay. So what I'm going to do is imagine one mole of copper. Okay. If it's 1 mole of copper, then N1 times N2 times N3 is equal to a big N, which is a total number, but that big N happens to be Avogadro's number. Okay, because a mole, remember, is defined to be the amount of substance. And specifically, the amount of substance is a numerical count of the number of atoms, if you're talking about mole of atoms, or the number of molecules, if you're talking about the mole of molecules, or like I said, the mole of moles, if you're talking about a mole of moles. So anyways, we're going to say that N1 times N2 times N3 is equal to Avogadro's number. Now, what we can do is say, I also happen to know that 1 mole has a total mass equal to 63 grams. Okay. That's the same thing as 0.063 kilograms. So just looking at it from a unit standpoint, if I took M total, which is measured in kilograms, and I divided it by the density of copper, which is measured in kilograms per cubic meter, this would give you the actual volume of the copper block. Okay. So, in other words, we would get cubic meters out, and you could actually recognize this as some number of cubic meters as the volume. So let's do that. We're going to say 63, or excuse me, 0.063. Divided by 8.9 times 10 to the third kilogram per cubic meters. Now, if I take my calculator and divide that, if I take my calculator and first turn it on, then I can divide that. So I'm going to say 0.063 divided by 8.9 times 10 to the third gives me 7.079. Obviously, that's 2 extra sig figs than we actually had. And that's times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 6 cubic meters. That does not seem right. 0.063 divided by 8.9 times 10 to the third. Yeah, something. Oh, excuse me. It's times 10 to the -6. What a goober. I just wrote it wrong like a dummy. Okay, so that's the actual volume. So the volume, by the way, suggests that you could say it's L. So in other words, we're going to say this length is L. And if we assume it's actually cubic, then we can just say each of those has a length L. That's sort of the same thing as saying N1 equals N2 equals N3, right? So we can say the volume is equal to L cubed, and that would tell us that L is equal to the cube root of the volume, which is the cube root of 7.079 times 10 to the negative 6 cubic meters. So now I'm going to take that number that I just calculated and I'm going to raise it to the 1/3 power, because 1/3 is the same thing as taking the cube root. And what I get is 0.01920 times 10 to the negative, or actually I'll just leave it like that since I've already got the decimal in the right place. So that's meters. So in other words, if you want to convert this to centimeters, a 1 mole chunk of copper would be basically 1.92 centimeters by 1.92 centimeters by 1.92 centimeters. Everybody get that? Now, we're also going to say N is equal to N cubed, so that N, which could be equal to N1 or N2 or N3, or just the average of the three, that is going to be equal to the cube root of Avogadro's number, because we know the total number of atoms in this case is actually Avogadro's number. So with this, I'm going to say the cube root of 6.022 times 10 to the 23rd, and that's technically atoms per mole. So if I take 6.022 times 10 to the 23rd, and then I raise it to the 1/3 power, I get 8.445 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th atoms. In this case, it'll be atoms per side. Okay. So we know the side has a length of 0.0192, and we know it has roughly 8.4 times 10 to the 7th atoms on it. So if I want to find the distance per atom, all I have to do is divide that distance 0.0192 by the number of atoms, and that'll give me the atoms per side. So I go over here and say continued. That's going to equal 0.0192. I think I said 20. Yes, I did. 20 meters. And that's going to be divided by 8.445 times 10 to the 7th. Yes. Atoms per side. And when you do that, you say 0.0192 divided by 8.445 times 10 to the 7th. And that gives me 2.274 times 10 to the negative 10th meters per atom. So what that means, ooh, I wrote atmo. Instead of atom, I wrote atmo. That's cool. Okay, so what we see is you have a copper atom and a copper atom, and then the distance between them is L, which is 2.3 times 10 to the negative 10th meters, and that's exactly the right answer. That's the same thing your book got as well. Anybody have any questions on that? So that's one of the things we were able to do just by realizing that matter is made up of atoms. Now, again, we also made the conclusion that as temperature went up, the substance should actually expand. And it's not unreasonable. Well, before I move on, let me make sure. Does anybody have any questions about how I did that? I explained it quite a different way than your textbook does. This is an example just like the one in the text. So you can read that and you'll have another explanation. So between me on this video that you can watch as many times as you want, or me in previous classes where I explained it probably a different way, you can watch those as many times as you want. And then finally, you've got the example in the book where Giancoli tells you about how he did it. All of that should combine so that you can figure out some way to make it make sense, because this is a fair calculation for me to ask you guys to do on any test or midterm or anything. All of our tests are comprehensive, so I could ask you this at any point, even though it's the first chapter that we covered. So any questions before I move on to the next thing? Okay. So what I was going to do is go into expansion or thermal expansion. And this, for instance, is the reason why you've got cracks in the sidewalk. I don't know. I was OCD when I was a kid. So I also made quite a bit of pain in my life by trying to avoid cracks in the car and the concrete, not because I really was afraid that it would break my mother's back, just because I was OCD and I had these crazy things going on in my head. But that's exactly why those cracks are there. You put the cracks at a certain distance, and that part is weakened so that when the concrete slab goes to expand a bit, it breaks right on that crack as opposed to just any old random place. And since that crack was pre-planned, it should come off fairly straight and not be a problem. They do the same thing with roads. They've got a workaround for railroad tracks, but they do the same thing with roads. So what I'm going to tell you is that the change in length, remember we use delta to mean final minus initial change in. So the delta literally means change in, and then whatever variable comes after it, unless we explicitly tell you otherwise, that's supposed to be understood as the final L minus the initial L in this case. Okay. What I would argue, and I think you agree with me, is that the change in the length of a rod upon increasing temperature should be directly related to, in other words, thumbs up, thumbs up. Okay. So if one goes up, the other goes up. I think you would agree with me that if I had a 12-mile long rod at 20 degrees Celsius, and then I increased it to 25 degrees Celsius, that 12-mile long rod would increase its length by a certain amount. Now, if you compared that to the amount that a 12-inch rod expanded and going from 20 degrees to 22 degrees, I think you would agree with me that the change in length of the 12-mile rod will be markedly larger than the change in length of the 12-inch rod. Does that make sense to everyone? Anybody doubt that? So the way we implement that mathematically is we say that the length, the change in length, delta L, is directly proportional to the initial length, L0. Okay. Now, if I had two 12-inch rods made of the same material and they were both at 20 degrees Celsius, and one I raised to 22 and the other one I raised to 24, I bet you suspect that the one raised to 24 would be longer, or in other words, its length would change by a larger amount than the one I changed to 22 degrees Celsius. Do y'all agree with that scenario as well? Any objections? All right, so what that means is the change in length is also proportional to the change in temperature. Now, you also might find that we could measure some physical parameter of a particular substance. Let's say if we had a copper rod, we'd get a parameter for copper. If we had a steel rod, we'd get a parameter for steel. And what we find is if you subject copper and steel to the same temperature change, and using two identical rods, say both of them were 12 inches long and 1 inch in diameter, and you change them both from 20 degrees Celsius to 22 degrees Celsius, it's not very likely that they would be exactly the same length afterward. You would expect one to expand more than the other. And what we're going to do is we're going to say that that parameter is directly proportional to the change in length. So we're going to define a parameter called the coefficient of linear expansion, and we're going to call it alpha. So what this does is it allows us to make this proportionality into an equation by saying delta L is equal to alpha times L0 times delta T, where this is the linear, this is the linear coefficient of expansion. And it should have, of course, units of 1 over Celsius degrees or 1 over Kelvin. And in fact, your book has a table of these values in the actual body of the text. So in the actual body of the text, it has coefficient of linear expansion in a, oops, I was just searching for the table and evidently slipped by it by accident. Okay. It's in section 17-2, I thought, but I'm not seeing it now. Hold on. Maybe it's the next one. 17-4. So in section 17-4, it has the coefficient of linear expansion for aluminum, for instance. So for aluminum is 25 times 10 to the negative 6, and that is Celsius degrees to the negative 1 power. If you looked at brass, you'd find that's actually 19 times 10 to the negative 6 Celsius degrees reciprocal. Copper is actually 17 times 10 to the negative 6. And let's do steel, iron or steel. That's actually going to be 12 times 10 to the negative 6 Celsius degrees to the negative 1. And one that's really important now that you've seen the steel one is this one down here, concrete and brick. It turns out their coefficient of linear expansion is 12 times 10 to the negative 6. Anybody have an idea why the linear expansion being 12 times 10 to the negative 6 is a good thing for concrete? Okay, so we have built a huge nation, and the planet itself has buildings that are huge. You know, for instance, that tower in Dubai, I think it's like 150 stories or something like that. So some god awfully large building that's approaching a quarter of a mile or a half mile in height or something like that. A large part of why that can be done in many cases is because we can use reinforced concrete, or excuse me, reinforced steel or reinforced concrete. And what that is you can actually put steel in tension. So you take a steel I-beam, for instance, and you pull on it as hard as you can, where it's starting to try to stretch a little bit according to Hooke's law. And then you can, while holding it in that state of tension, you can actually pour concrete in a form around it. And since concrete and steel have the same linear coefficient of expansion, once it dries, they're going to expand and contract by the exact same amount. So the actual bonding between the steel and the concrete shouldn't be disturbed too terribly, at least for a long period of time. So that's the big reason why that's important. That table, by the way, has liquids as well. which is kind of an interesting thing. And it has gases too, but you're going to see there's a marked difference. So for instance, in going from solids, which is on the order of 10 to the -6, to liquids, that is also on the order of 10 to the -6, but the mantissa of the scientific notation is like 950, 1100 for ethyl alcohol, or 500 for glycerin. And if you go to glass, it's more, or excuse me, to a gas, it's more like 3400 times 10 to the -6. So you can see it's a factor of 10 going from solids to gas, or excuse me, solids to liquids, and then another factor of 10 at least going from liquids to gases. Okay. Now there's equivalent formula. If you attack this particular equation, you'll find that equation works quite nicely. And I pretty much just use this one, but your book gives another version that's quite nice. So if you break up that delta into L minus L0, where L is supposed to be the final length, is equal to alpha L0 delta T, you can then say L is equal to L0 plus alpha L0 delta T, or finally you can say L is equal to alpha, or excuse me, L is equal to L0 times 1 plus alpha delta T. That's the other version that your book uses. And application of this is pretty straightforward. I'm actually running out of time, so I will at least point you to some calculations I've done, but what I'm planning on doing is actually continuing next time with this chapter 17, and I've already pushed your homework back to Wednesday. I will tell you, in principle, you could do another one for the area of a chunk of substance. So you get the change in area is equal to some quantity times the initial area times 1 plus that quantity times delta T. So I might say A is equal to A0 times 1 plus, let's say, gamma delta T. But it turns out when we do that, that gamma is really, really close to 2 times alpha. And we can go further, and it turns out we can also say that the volume expansion is equal to the initial volume times 1 plus beta delta T. And it turns out that that beta is approximately equal to 3 times alpha. So this is another equation that you can use. For instance, your book does a problem where it asks you, you fill up a gas tank with gas. The gas tank's made out of steel and it holds X number of gallons. You fill it up with gasoline, which is X number of gallons, and then you allow the temperature to change. You go from, say, 10 degrees Celsius to 20 degrees Celsius. And of course, in going an increased temperature, the actual volume of the hole in the tank, in other words, the part that the gas fills up, that increases in size because it turns out that's the way matter behaves. A hole in a substance and an object will expand the same way as the object itself does, just as if it were filled in with that same material. So the volume inside of the tank is going to expand just like it was a chunk of steel equal to that volume. And then the volume of the gas is going to expand as well. And you can see that they do that at different rates. So it asks you, is there any overflow of the gas, or is the gas actually less full? Is the gas tank now less full? That kind of thing. So that's a problem you can work with the V version. But remember, you also have the original version, which is delta V is equal to beta V0 delta T. So that works as well. And of course, there's a similar one for the area one, but that's one of the equations you can use. Now you know how to use it. I only got like 2 minutes left, so I want to give you a little bit about the ideal gas laws so you can start on that. The first ideal gas law we'll talk about is Boyle's law. That's the scuba diver's law, and that's pressure and volume are inversely related. So that means when the pressure goes up, the volume goes down. It's thumbs up, thumbs down. Okay. So that's Boyle's law. Then there's Charles's law. And Charles's law says that when the volume goes up, or when the temperature goes up, the volume goes up. Now, we're talking about here equations of state, which your book talks about. You need to read that, but we're looking for the minimum number of parameters that define a system. In this case, we're talking about a system that is a gas that we're pretending like it's ideal. So it turns out we can fully understand an ideal gas, at least by knowing its pressure, volume, and temperature, and R, its pressure, volume, and number of moles, or its pressure, temperature, number of moles, and so on and so forth. So we ultimately get an ideal gas law that relates those quantities: pressure, volume, number of moles, and temperature. These observations that were made here by Bull and Charles were basically in the case of a constant temperature, the volume is inversely related to pressure. So it's important to realize that T and N, the number of moles, equals a constant. And here we can say that the pressure and the number of moles equals a constant for Charles's law. And then we have the Gay-Lussac law. And I'm drawing a blank on spelling that. I think it's Lussac. Gay-Lussac's law basically says that pressure and temperature are directly related. And of course, in that case, we have to have the volume and the number of moles equal to a constant. Okay? If you put all that together, you ultimately can say all of those things along with a further understanding that, hey, if I add more molecules into a fixed volume, that's going to increase the pressure. So that alone can tell you that the ultimate expression is going to be PV equals N times some constant times T, where N is the number of moles, R is the ideal gas constant, which in physics we almost always use as 8.314 joules per mole Kelvin. But it turns out if you want to use some other units, there are some other gas constants that are very helpful. For instance, there is a zero. Ooh, my pencil just stopped writing. I think my pencil might have died. It does look like the battery's dying. Yep, the battery has died on my pencil. So I will tell you what those other values are. I do not have an extra pencil. So the other values you can find in your book too, but one of them is 0.0821, and that's in liters, atmospheres, moles, and Kelvin, liters times atmospheres divided by moles times Kelvin. And then the third one is 1.99 calories per mole Kelvin. So all of them have the mole Kelvin at the bottom. But if you want to use pressure in atmospheres and volume in liters, you can use the 0.0821. And if you want to use things like different units, I think in that case, you're going to use cubic centimeters. If you use cubic centimeters, I think you can ultimately get the 1.99 calories per mole. To be honest with you, I haven't used the 1.99 in a long time. I'll just tell you that 1.99 calories per mole Kelvin is another version. The key thing to remember also is that T has to be measured in Kelvin. It cannot be in anything else. Okay, so we're done. I'm sorry I didn't get more done. I may post some videos over the weekend. If you've subscribed to my YouTube channel, then you will automatically be notified if you've got the notifications set up when I do post stuff. That's why I recommend you do subscribe to my YouTube channel. But either way, like I said, I might put some more videos up tomorrow and this weekend. I'm not certain that, but at least you have access to some where you can go ahead and start and see everything I've ever covered in chapter 17. So if you've already sent me an email, sent me a chat with your first and last name in it, then you guys are free to go. And that's about it. Anybody have any questions? I'll wait here till the last person leaves in case anyone does have questions.
I have a question. Everything like today seemed pretty basic, but I have a question like regarding lab on Tuesday.
Uh-huh.
So I went and met Denise today, and she told me that she's like not actually our lab instructor. Her name's just up there like until somebody else is hired.
Right.
Tuesday, this like 2 days ago's lab was canceled, correct?
Right. Yeah.
So, okay, I'm gonna have to miss next Tuesday's lab, but I don't know who to email because I don't know who the professor's gonna be.
Gotcha. We know who the professor is going to be. It's not like we're that far behind. It's
Okay.
just the problem with he doesn't have his account set up so they can use Canvas and all that stuff yet. So we can let him know about you, Hannah. If you can find some way to fit in my lab, you're welcome to do that one in lieu of that lab since you're going to miss one. But you don't have to, of course. You're always allowed to miss one lab anyways.
What day is your lab? Is your lab the Monday?
Yes, you're in 242, so my lab is Monday morning at 9 a.m.
Yep, crap. I have class from like 9 to 11:50, so I cannot make that one.
Not a problem. It's not a big deal. Like I said, people just have to miss lab. The good news is, well, the bad news is you weren't aligned with the day he had to miss. So now you're going to have another one that's going to be missed. But that's okay. Like I said, almost all instructors I've ever met allow at least one missed lab.
Okay.
And there might even be a way, if depending on what lab he does, sometimes there's a way where you could do it on your own, even without the lab. So you might ask him about that. And if he has any questions, he can ask me or Dr. McKay, who's Denise that you mentioned. He can ask us, and we have ways of helping him if he needs it.
Okay, perfect. Alrighty. I don't do y'all know like when our canvas will be posted or like when he'll have his account yet, or you're just kind of waiting on like the higher ups and with TCC administration for that?
Yeah, we're waiting on administration and IT.
Okay.
I suspect he should have it by tomorrow. And I have been told that he will be using Canvas for the lab, so you should see one pop up all of a sudden. So hopefully that'll work out. But don't worry, we got you covered. If he doesn't show up, we'll have someone to fill in or whatever. But I can't imagine he wouldn't show up.
Okay.
As an
Alrighty.
additional sidebar,
Yeah, go ahead, Jacob.
um, are we, I guess, still having class on Tuesday?
Yes.
I
Yeah,
guess not
class
here.
is
Sorry, the
still
lab,
going.
I should say. Are we planning on having lab on Tuesday?
So far, yes, there should be no problems with lab. Everything should be ready to roll in lab. You don't need anything a priori for your lab because we actually distribute the lab write up to you guys. We used to actually print them out and give you a print copy. Then we got kind of poor, so we started making you pay for them to be printed. And then us as a department sort of did a mutiny, and most of us, I know I do, I've decided not to print anything. So I give you an electronic Word version and you just fill that document in and turn in an electronic version. So you're not missing anything. Even if he doesn't tell you anything up until you show up in class, you'll still be okay with walking right in anew.
Wonderful. Okay, thank you.
All right. That it, everybody?
Yep. Thank you.
You're welcome. Glad to see you again, Hannah. Take care, Jacob.
Nice to see you. I'm looking forward to this semester.
All right. See ya. Have a good one.